Sorry about that. Sorry about that. Anyhow, let me start again. Such electron microscopes cannot provide in situ way of seeing something, seeing what's going to happen in the realistic biological system. Right? That's the reason why many people prefer to use the optical microscope rather than electron microscope. But as you already learn about that, this optical microscope commonly suffering from the diffraction limit, right? Diffraction limit. So what that means that the focusing of the light, which are required for imaging something, is highly limited to the half of wavelengths, right? So, for example, optical microscope based on the visual and near IR, right, can be focused and with the minimal feature size about the 200 nanometer or 300 nanometer, etc. So, below this size limit, we cannot see anything, right? So many people trying to overcome this kind of challenge in the field of optical microscope, and this motivation drive the development of the specific field called super resolution optical microscope. Super resolution optical microscope. So by which we can overcome the diffraction limit. And eventually, in this day, many guys working in the super resolution microscope field can see molecular something through the optical microscope, even through the optical microscope. So in this day, if we can benefit from the super resolution optical microscope technology, we can resolve the about the few nanometer scale something. For example, 4 nanometer and 5 nanometer resolution will be allowed if we can use the super resolution optical microscope. That also can be basically achieved through the self-assembly technology. So we're gonna see what's the thing also in this chapter. As well as building up the tiny molecular machine and super resolution optical microscope technology, many other things also can come up with this self-assembly technology. Okay. So this slide also already given to you guys, and maybe you already remember what's that mean, right? So basically previously we start with it here, and then took a step toward a much smaller thing, and this kind of the making smaller thing has been achieved through the lithography technology, right? So we can say that this top down, and also by using a lot of individual building blocks, and then we can induce the assembly of these building block toward a specific structure like this. Okay, so that's the reason why people say that we're gonna start from the bottom and then we're going to up. That's the reason why people say that bottom up method, and this bottom up method is represented by the self-assembly method. Okay, so to start, let me introduce the major motivation of the why we have to do some sort of self-assembly. So, have you seen this slide? It's quite a famous slide which can be accessed in the website. And so you could put some keyword of the molecular machinery, and then you can get access to this slide. So this slide is summarized what kind of molecular and biological machine can be found in the our body, right? So as you already know, we can start with the DNA, and DNA within in the DNA, we can see some sequence of base, right? You already familiar with what's the ATGC of DNA, right? Adenine, guanine, cytosine, thymine, and according to the sequence of these base, we can genetically encode specific information, okay? And such genetic information encoded by the sequencing of base of DNA can be translated into the RNA, and then RNA also the genetic information of RNA is further translated into the amino acid sequence, right? So there are 20 major amino acids, right? For example, thymine, etc. So such 20 number of the amino acid can be specifically sequenced according to the genetic information, and then according to this kind of amino acid sequence, peptide or protein can be actually eventually obtained. And according to the sequence of amino acid, this protein polymer is some sort of polymer, right? Polymer going to be entangled and folded into specific shape and structure. So according to the specific shape and structure of each protein, their functionality can be defined, right? So in this, let me turn on this movie. So, according to the structural function, there are a lot of protein can be found, and this slide can summarize what kind of protein which have that specific function in there. Okay, so photosynthesis, energy production and storage, enzyme, etc. Okay, so if you click on it, you can see more detailed structure of each specific individual protein. So let me repeat this. According to the shape and structure of this protein, their functionality can be specifically and programmably defined, right? The other thing I would like to emphasize here is that this molecular machine actually has incredibly complex structure in three-dimensional way, okay? Okay, along the x, y, z axis, their structural complexity is incredibly high, right? Particularly compared with what we can make up structure particularly through the lithography method. Okay, so basically, as you already learned, lithography is compatible with two-dimensional method, even if soft lithography is not, right? But this is basically limited to the two-dimensional method. Okay, yes, of course, software software allows to overally bend and globally bend the patterned surface, right? So we can put the patterning on the curvilinear surface as well, but this kind of three-dimensional complexity cannot be assessed even through the soft lithography, right? But biology or other naturally occurring material can do and can achieve this kind of three-dimensionally complex structure, and we're gonna see how we can achieve it. Okay. Frankly speaking, I need to say that at the moment, our ability to do such self-assembly cannot be matched with what nature can do at the moment. But the field of self-assembly, artificial self-assembly, I would like to mention, have been rapidly increasing and growing. So many of aspects of the artificial self-assembly getting more close to what nature can do at the moment. So we're gonna see also how we can do this kind of the similar job what natural occurring material can do. Anyhow, I would like to say that this naturally occurring biological machine is outcome of the self-assembly, and through this kind of self-assembly at the molecular resolution, they can achieve incredibly complex structure. Here, protein assembly. and through that, which in turn they can conceive the awesome power to do some sort of machinery, right? For example, this coronavirus also can be considered as the biological machine, okay? They can have specific function. So as you already recognize, the surface of the coronavirus is consisted of the spiky protein, right? Spiky protein. It globally has the spherical shape, and each surface is protruded with the spiky protein. And this each spiky protein can be programmed to directly contact and connected with the receptor protein in the cell membrane, and through that they can get into the inner cell, okay, inner of cell, right? And then their shell within the cell can be programmed to be deassembled, and the genetic molecule like the DNA and RNA, which are initially within the empty space of the virus shell, can get out from the shell, and they can start to specific function within the cell, like the infection and interfering genetic process, etc., right? So overall, we can say that such virus also can act as a robot or machine, right? According to molecular machine, okay, according to their structure, okay. Okay, so here's the photosynthesis 2. So here is the protein can be found in photosynthesis 2. Which can receive and harness the incoming sunlight, and this incoming sunlight can activate the specific molecule within this protein. So the specific electron in the specific molecule can be excited when this protein harvests the light, and then the charge can be generated within the molecular complex in this photosynthesis 2 protein, and then the generated carrier can be programmed to be cascaded along this molecular assembly, and they can eventually participate in the chemical reaction, and then specific chemical can be generated. So this is basically ingredient for all the living creature in this planet. Okay. And such functionality also can originate from this complexity in molecular assembly, because photosynthesis to protein assembly. Okay. Also, let me introduce another good example. Okay, so here is the quite famous movie produced by the Department of Biophysics at Harvard, and they created quite beautiful animation on what's going to happen in the cell. So some guys say the cell is the microcosmos. So there are a lot of components which are very closely related to many physiological property in our body, right? So each molecular motion do some sort of specific function, which are essential for maintaining our biological function, actually. So I'd like to strongly encourage you guys to see this movie at the YouTube. You can put the keyword of inner life of the cell, and you can see, okay, here is the lipid left. Okay, so it also has quite complex molecular structure. Okay, so we can see three-dimensional complex structure characteristic with the molecular resolution, and they are programmed to bind to the protein molecule, receptor molecule located at the lipid bilayer. That's actually cell membrane. Also here, chemokine, proteoglycan. Also later on there will be some my favorite, that's motor protein. So please stay tuned until the motor protein come out. Okay, so here is also actin filament, and we can see the receptor protein or ionic pump channel in the lipid membrane. And such lipid membrane is boundary which can divide the outer of the cell and inner of the cell, etc. And also see a lot of micro component in within the cell is connected through the microtube, also called the actin filament here. And also I would like to emphasize that each component has each different shape. What that means is that each different component has each different functionality. Here is the active pyramid. That's one of my favorite in the cell. Which can act as a mechanical supporter for maintain overall shape of the cell here. Also, as well as a mechanical supporter, this active filament can act as a channel for transducing the chemical signal within the cell. Also, I'd like to mention that this actin filament is the outcome of the self-assembly process. Actually, specific protein designed to be self-assembled into this kind of tubular shape, one-dimensional tubular shape. Also, solving protein can act as a disconnect the actin filament like that. Okay, so already assembled actin filament can be deassembled when they meet with solving protein, as indicated here. Also, here is the another good example how this microtubule can be assembled, right? Specific protein can be programmed to be assembled into tubular shape with the empty space. Okay, it's some sort of the coshel type to the microtubule. Okay. Also, this microtubule can be deassembled. Also, here is my favorite. That's motor protein. As I mentioned just now, this motor protein can hold the vesicle. Within the vesicle, we can see some specific chemical which to be transmitted. Okay, so as you look at here, this motor protein has two legs and two arms, so they can actually walking around the actin filament surface. Also, they can hold the vesicle for transporting the chemical signal. Here is the mitochondria. Mitochondria is one of the important component within the cell, which can store the energy in the form of ATP, ADP. Okay, ATP can be stored in the form of ADP in the mitochondria, and when they are converted into the ATP from ADT, they can emit the specific energy. Okay, so that's the one of the fundamental to maintain our biological energy, etc. Here is the another important biological machine. That's the ribosome. Okay. So they can receive the genetic information from the DNA, and then they can translate the genetic information into the form of RNA, and then this is going to be translated into the amino acid sequence in the specific protein polymer, and this protein polymer going to be folded into specific shape. So as the full time of this movie is about the 8 minutes, so it's pretty long. So I'd like to encourage you could see this movie through the YouTube. So I still believe that you guys, if you are interested, can go to the YouTube and put the keyword of the inner life of a cell, and then you can see the full version of that movie by yourself. Okay. Anyhow, I'd like to mention that the structural complexity found in such biological molecular motion is incredibly high, and far much more complex compared with, particularly compared with what we can achieve through the lithography method. Okay, so left panel in this slide is representative example the far most complex structure which can be would be accessible with the conventional lithography method. Okay, but the complexity, structural complexity, and the resolution of this lithographically defined structure cannot be matched with what the structure what the naturally occurring material can achieve. Naturally occurring creature can achieve. Okay. So so you guys already saw many of the example, right? For example, the many molecular machinery in the cell or other common biological fluid. Also, to finalize the importance of the molecular machine, structural complexity of a molecular machine, Let me give you another example. Here is another favorite, my favorite. That's the bacterial flagelar. Okay, so if you look at it more closely, they are mainly consist of two components. One is the body, and the other one is here tail. Interestingly, here tail is can be rotated. Okay, can be rotated, and then these bacterial flagella can swim within the fluid. They can go along the specific direction. Okay, that's the amazing thing we can see from this wonderful example of the bacterial flagella. So let me close up this connecting part between the tail and body in here. Okay. So what you can see here is the tail is hanging out from the body, and if you look at more closely this connecting part, you can see that this tail is screwed. Okay. So and this screw is connected through specific rotor like this. Okay. So from here to there, the scaling. So let me give you idea about the size of this molecular rotor or motor. So that's about the 30 nanometer. That's actually quite small scale, quite tiny machine. But amazingly, we can see several number of gear here. Here are coaxially stacked and rotated each other. Okay, so this gear, this assembly of several gear is programmed to be rotated in a highly precise way. So this molecular gear can receive the ATP, and as I mentioned just now, this ATP is the origin of the energy from our body. So when they receive the ATP, they can be powered. They can be powered to be rotated along this main axis like this, and then eventually this tail can be rotated. Okay, so as you look at it, this is has a screwed form. Okay, so this is going to be screwed. So this bacterial flagella can be empowered to swim along the specific direction. Okay, so one of a good example of the molecular machinery. And I would like to say that, can you conceive the idea how we can build up such kind of quite small, tiny machine, even with the lithographic method? Okay, so I don't like to say that that's not impossible with the lithography method, because nobody know at this point. Some guys in the future could successfully build up such molecular machine even with the lithography methods, but I'd like to mention that at this point it's quite highly challenging to materialize such kind of quite complex and molecular resolution, quite complex molecular machine with the molecular accuracy. Okay, and that's the main reason why we need to switch up the gear toward the bottom-up method rather than top-down method. Okay, so as you might feel that it's quite highly challenging to achieve this kind of molecular machinery with the lithography method. First, we need to overcome the resolution limit of the currently accessible available lithography method, right? So even with the electron beam lithography, some achieving a few nanometer resolution is highly challenging, right? Highly challenging. How about the photolithography, right? EUV, extreme UV lithography, right? Extreme UV lithography itself cannot reach at a few nanometer resolution, right? So as I mentioned before, this currently accessible minimum resolution from the extreme UV lithography is limited to tens of nanometer, right? For example, 30 nanometer and 4 nanometer. okay, on the specific circumstance of the light-based lithography. For example, we need to suffer from this diffraction effect, right? So even in the extreme UV light source, it's quite challenging to go beyond the resolution of tens of nanometer. Okay, so in order to go further in terms of resolution breaking, we have to do some sort of additional lithography, like the quadruple lithography, etc. Right? So once we have the pattern feature defined by the extreme UV method, we can go further through the quadruple patterning method. Okay, so initially the pattern resolution is limited to 30 nanometer, 30 nanometer, and 40 nanometer, and then this can be further reduced to a few nanometer scale through the multiple lithography, like the quadruple lithography, etc. So at the moment, it's nearly impossible to achieve such molecular scale. Also, with the far advanced lithography method, it is quite challenging to achieve three-dimensional structural complexity, much like the bacterial flagelar motor, right? So, due to this challenge from the lithography method, I would like to say that we need to switch up the gear, particularly for the self-assembly method. Okay. So before going further, let me briefly introduce what's the self-assembly. So the definition of self-assembly in this lecture will be further elucidated through the rest of this semester lecture. But before going further, let me define what's the terminological definition of the self-assembly. What's the self-assembly? Self-assembly means that some building block can be assembled by themselves. Okay, that's the reason why I do like to say that that's a spontaneous process. Okay, spontaneous organization. Okay, so building block can be widely ranged from this nanoparticle or molecule to molecule. And doesn't matter what kind of building block going to be assembled in here, but first we need to focus on the spontaneous organization. Okay, spontaneous organization. What that means that each building block going to be assembled by themselves. Okay, assembly means that first the building block are initially randomly dispersed in specific medium, or they can be initially randomly dispersed onto the solid state substrate. Doesn't matter. What I want to say, the initial stage is generally the randomly dispersed building block, right? And on the specific condition where the thermodynamically favorable state, initially randomly dispersed building block going to be assembled into specific pattern or specific structure, much like the biological component found in your body. Okay, so we can say that self-assembly is the spontaneous organization of the building block according to thermodynamics, and this process can be assembled by themselves without any kind of invasion. That's the reason why I added this without human invasion. Okay. So according to the specific thermodynamically favorable state, the initially dispersed and randomly dispersed building block can be assembled into the pattern or specific structure, much like the protein machine found in our body. Okay. And through the self-assembly, we can achieve the unprecedented structural complex in three-dimensional way, which would be difficult to achieve with the conventional lithography method. Okay, so let me introduce some funny example. So this movie is actually taken from myself. Okay, so what you are seeing there, here is the wallet, and each wallet is randomly assembled and aggregated at each state. So what's we gonna see what's going to happen when I put some enough thermodynamic energy. What I mean by that, I'm going to put some enough kinetic energy to induce the motion of each wallet, and then we're gonna see what's going to happen. Okay, so by shaking them, we can put some put some more energy. So what's going to happen is that all those spherical wallet going to be assembled. Okay, if you look at it more closely, this each individual wallet are going to be assembled into specific lattice. That's actually hexagonal lattice, right? So even if here, you can see that the size distribution of each size of each individual wallet is highly dispersed, right? So size of wallet are not so uniform. That's the reason why the long range order was not achieved in this case. But anyhow, what I like to emphasize here is that this initially fully randomly aggregated spherical wallet going to be assembled into the ordered state. At least we can see it on range order, right? Okay, that's the self-assembly. That's the flavor of self-assembly. Okay. And here this is a macroscopic scale. So we can imagine that this overlay can be reduced to the molecular scale, and we can induce the similar situation. Actually, the molecular or even nanoscale particle can be randomly organized, randomly aggregated and dispersed in a specific fluid, and under specific condition where the thermodynamically energy state is thermodynamically minimized. This building block going to be assembled much like this one. Okay. As well as this kind of the array or pattern, three-dimensional assembly, complex assembly, much like the biological machine found in our body, also can be achieved, as we will see rest of today's lecture. Okay. So it's already been 40 minutes, so 1:41. So how about take a rest for about 10 minutes? So we can start at 1:55. Okay, so see you soon. Thank you.